All right, section 2.6 deals with derivatives and rates of change. And what I'd like to do to introduce that section is to actually go into the ebook and look at the ebook for just a little bit here. So let me bring up the ebook. And you also can go into your ebook, but I'm going to display it here for us. Okay, limits and derivatives, chapter 2. And we want section 2.6. Derivatives and rates of change. So you notice that taking limits are pretty important in this course. The problem of finding the tangent line to a curve, and you were interested in that with your assignment last week. Okay, the assignment was from, let me see here. It was actually earlier, the limit of a function where you were finding like secant lines and so forth, and then, you know, what's the slope of the tangent line going to be? So the problem of finding the tangent line to a curve and the problem of finding velocity of an object both involve finding the same type of limit. As we saw, okay, in section 2.1, this special type of limit is called a derivative. And we can see that it can be interpreted as a rate of change in any of the sciences or engineering. Hold on here, there were a few chat comments. Yeah, so John, right now, I deactivated the assignments right now. Don't worry, they'll be coming back. Okay, all right. I don't want you to be tempted to not listen to the lecture, right? And but do not worry. Okay. And I would do the same thing in a face-to-face class. Believe me, I do. All right, good question. Good question. All right, so let's see here. Okay, so tangents. So you have learned that the slope of a tangent line, if you have a function f of x and you want to find the tangent line to a curve C at a point, and we'll just call it, we'll say it has coordinates a and f of a. Well, we can consider a nearby point to the coordinate a, f of a. We'll call it x, f of x. The slope, okay, between these points P and Q would just be f of x minus f of a over x minus a. And they have a little picture there. So the blue in figure 1, the top graph, the blue line segment is the line segment going from point P to point Q. Okay, the rise between the points is the difference of the y values. That's going to be f of x minus f of a. The run is going to be the difference in the x values, and that's going to be x minus a. So that's why the slope of the line segment, or the secant line going through the points P, Q, is f of x minus f of a over x minus a. And what they're doing in the second graph of figure 1 is they're saying, well, what if we were to move the point Q closer to the point P? As we move the point Q closer to the point P, and we look at these secant lines that go through the points P and Q, as Q approaches P, the slope of this, as Q approaches P, the secant line approaches the tangent line T. So the slope of the secant line as Q approaches P will approach the slope of the tangent line at P. Okay, the tangent line to the curve C at the point P. Are there any questions on figure 1? Are there any questions on what they're doing there before we move on? Okay, hang on here. All right. Excellent. Thank you, Nicholas. Thank you, Ian, Anna, Lynn. Excellent. James, excellent. So John says a more closer Q is to P, more closer to the tangent. That's right. That's correct. That's exactly right. Okay. So now what we can do then is we can say, well, this brings up a definition. Now I want to try something here. No, I don't want to do that. Okay. So the definition of this tangent line then, we want the slope of that tangent line, that red tangent line in the figure. The slope of that tangent line would be the limit of f of x minus f of a over x minus a as x approaches a. That would be the slope of the tangent line. Okay, that would be the slope of the tangent line. And that slope is called a derivative. That slope is called a derivative. Okay. So in example 1, they want you to find, well, are we okay with this definition here that the slope of the tangent line would be the limit as x approaches a of f of x minus f of a over x minus a? Are we okay on that? Okay, all right, one moment. So people are comfortable. Let me re-explain it just again here. So what we're doing, we are interested, you see here you have a curve, a function, and you have a point P on the function, and they've drawn a red tangent line. They've drawn a red line in figure 1 here on that graph. That red line is the line that is tangent to the function at the point P. And we are interested in finding the slope of that tangent line. How are we going to do it? Well, what we're going to do, we know that to find the slope of a line, we need 2 points, a point P and a point Q. The point P is fixed. That point is fixed. That doesn't change. But what they're doing in the figure 1 here, the second graph, is they're changing the point Q so that it's approaching the point P. The secant lines, the blue secant lines, therefore, are going to approach the tangent line. And this means that the slope of the secant lines approach the slope of the tangent lines as x approaches a. And that's what they're reinforcing in the definition, that the tangent line to the curve y equals f of x at a point a f of a, okay, which is a point on the curve, is the line through P with the slope. M is the limit as x approaches a of f of x minus f of a over x minus a, provided the limit exists. Okay. So let's get to an example. We want to find the equation of a tangent, and here's the definition. Okay. So we want to find the equation of a tangent line to the parabola y equals x squared at the point 1, 1. So 1, 1 is on the parabola y equals x squared because 1 equals 1 squared. So what they do is they use the definition above, and they say, okay, Well, the slope of this tangent line is going to be the limit as x approaches 1 of the quotient f of x minus f of 1 over x minus 1. Some of you might have seen this quotient in pre-calculus. Has anybody? Usually it's talked about a little bit in pre-calculus, but you don't know maybe its importance. But how many have seen that in pre-calculus? Computing a limit like that. I know I taught it when I taught Math 165, but all right. Well, at any rate, so we are looking for this limit. It's been a while for Lynn. She remembers it, but it's been a while. So okay, we're gonna find this limit here. So f of x is x squared. So I have the slope is the limit as x approaches 1, and this is a two-sided limit, by the way. We could approach 1 from the left or from the right. Okay. We factor the x squared minus 1 in the top. Then the x minus 1 and x plus 1. The x minus 1 simplify out, and you get 2. And so the equation of the tangent line then is going to be y minus 1 equals 2 times x minus 1. That's using the point slope form of a line. All right, are there any questions in regards to getting the tangent line? This is why you've been learning about limits, for the past week, is because the definition of a derivative is based on the limit of a quotient. All right, well, so then what they do here then is they show the graph. They show this graph of the parabola. Okay. They show the graph of the parabola in figure 2, and they zoom in on it. Okay, so if you look at the point 1, 1, and you adjust your window, you see, like in the first graph in figure 2, the x goes from 0 to 2. The second graph, so it has a width of 2. The second graph, the x goes from 0.5 to 1.5. So that window has a width of 1. And then the third graph, the window, they're letting go from 0.9 to 1.1. So the width there is only 0.2. So you're closing in, you're zooming in on the coordinate 1, 1. And my question is, what does the graph appear to look like in the third picture there in figure 2? What does the graph appear to look like? That's right. Excellent. John, Ian, and Betsua. It's a straight line. And that would make sense because there is a line tangent to the curve at the point 1, 1. And that line has the equation 2 times x minus 1. And that would be approximately equal to that almost looks like the tangent line in the third picture. So that's one of the big things you're going to do in section 2.6 is finding slopes of tangent lines. 2 points on a curve, and then finding the equation of the tangent line. Now, the definition of a derivative can be altered. Okay, if we go down here, it says here there's another expression for the slope of a tangent line that is sometimes easier to use. If you were to let x minus a to be equal to h, if you were to let x minus a be equal to h, so in other words, in the previous definition for the tangent line, the slope of a tangent line, you're going to replace x minus a in the denominator with h. But that means you're going to replace x with something different as well. Because if h is x minus a, then x is a plus h. And so the slope of the secant line will be equal to f of x minus f of a, but x is a plus h, and then then the denominator is h. Okay, so what they're doing now is, in figure 3, they have the same tangent line at the point P that you saw earlier in the figure 1. Okay, but they're letting Q. They're going to let Q approach P, but the coordinates of Q are not x fx anymore. They're a plus h and f of a plus h. And as you let h get small, the q coordinate will approach the p coordinate. And therefore, the slope m of the tangent line at the point P is going to be the limit as h approaches 0 of f of a plus h minus f of a over h. This is the alternative definition for the derivative. Okay, so you have two ways to find the slope of a tangent line, different ways. Sometimes we use one way, sometimes we use another way. It really depends on the application. Now I'd like to show you how this slope here works for this one, the second one. We'll look at an example. Yes, John, both will have the same answer. It will not matter which definition you use. Both will give you the same answer. Absolutely. Excellent question. So here, they want you to find the equation of the tangent line to the hyperbola, y equals 3 over x. This is example 2. Find an equation of the tangent line to the hyperbola, y equals 3 over x at the point 3, 1. So what they're doing then is your function is 3 over x, and x is 3 plus h, a is 3, and they just apply the definition. They just apply the definition. Take a look at it for a moment, because this would be the first time most of you are seeing this. Are there any questions on what I have on the screen in terms of at the bottom there, m equals the limit as h approaches 0 of f of 3 plus h minus f of 3 over h? Are we okay with what they're showing? I'll just comment here, going from the numerator, they have 3 over 3 plus h minus 1. What they're doing is they're writing 1 as 3 plus h over 3 plus h. And then you have a common denominator. But we still need to compute the limit as h goes to 0. And so we do a little simplification, and we'll get negative 1/3. And therefore, we get the equation of the tangent line. All right, so what I'd like to do in the last 5 minutes of class is I'd like to have you work, hold on here, on 2.6 just a little bit. Okay, so in All right, so are there any, I mean, I know that this is new to you, so, you know, and I want to give you a little practice. John says, how come the other way of finding the slope of the tangent is so close to finding the formula for the difference quotient? Well, actually, both formulas are the same as the difference quotient. It's an excellent question, but what they're doing is, remember, they let, for this second, hold on here, one moment. For this second slope definition, they had let x minus a equal h. So x was then equal to a plus h. So all they did was they took here, they took the original definition that you learned, the original difference quotient, and they replaced x with a plus h. And then x minus a was equal to h. So it's just they're just rewriting the difference quotient to get this second definition. All right, very good, very good. All right, so take a few moments. Let's just see if you all can, I have the section 2.6 exercises showing in WebAssign. You should take about 5 minutes and just see if you can get the first question right. Okay. Let's just see if you can get the first question right. I'm going to stop sharing this here. So 2.6 is visible. Of course, we're going to talk more about 2.6 on Wednesday, but we like to use every minute class, right? Okay, so let's see if you can get through example 1 here. And I'll stop the recording.